Now you know that the idea of impulse, it comes from Newton's second law. Now the way we wrote Newton's second law was this. We wrote F is equal to dp by dt, where F on the left hand side as well as dp on the right hand side are both vectors. And this is in fact Newton's second law, which for the special case of an object of a fixed mass can be shown to be equal to F is equal to ma. Fine. But then for any other case, for any general case, F is equal to dp by dt. Now this term here, F dt, so if I bring in this dt over to the left hand side, I end up having F dt is equal to dp. And the term on the left hand side is some force acting for a small amount of time dt, and that is equal to a small change in momentum of the object. And this term, F dt term, has been given a different name. It's called impulse. We have also defined a new symbol for it, J. So I can say that this F dt is impulse of a force F acting or over a time dt. And this is equal to the small change in momentum dp of the object on which F acts. Over a time dt. So a very simple thing, J is equal to, so we say that J, which is the impulse of a force, is equal to F dt. Now impulse happens to be a vector because we have got a force here which is a vector, so J will also have an arrowhead over it. It is also equal to dp, p is a vector. So overall, keep in mind that impulse is always a vector. Now if I want to find out the total impulse of a single force over not a small amount of time dt but over a large amount of time, and maybe this force is a function of time itself, then what I can do is, in fact I should write here dj, should not even write j. So for a finite amount of time, the total impulse is j, which is integral of F dt. And this force that I'm talking about, it may be it may be the only force acting on the object, or it may be the resultant of a large number of forces acting on the object. So there is always a chance that there are F1, F2, F3, F4, etc. forces acting on the object, and they give us a resultant F. And those forces F1, F2, F3, F4, etc. may be dependent on time, and so the resultant F may also be dependent on time. But then what I can do is, under that assumption, I can write this as F1 plus F2 plus F3 plus so on, and this entire term will be a function of time dt, which I can again break up into small pieces. So integral F1 dt plus integral F2 dt plus integral F3 dt and so on. So what this statement says is that if you have to find out the total impulse J due to a large number of forces, you can find out their individual impulses and then you can just add them up like vectors and you will get the total impulse. So don't go for a scalar addition, that's the only thing. Go for a vector addition and you can still add up impulses to get the total impulse. So everything that works for vectors then works for impulse. One thing that you will also immediately identify on seeing this expression integral f dt is that impulse of a force can also be found out by finding out the area enclosed by the force versus time curve with the time axis, of course. So suppose you have got x, y, graph like this, where on the x-axis I have taken time and on the y-axis I have taken force, and the force varies as a function of time in this fashion. And then if I evaluate the area of this curve between some time t1 to some other time here t2 perhaps, then that total area, this total orange shaded area, is going to give me the impulse of this time varying force in that amount of time t1 to t2. So therefore area under the graph is integral of f, which is a function of time, times dt, and the limits here will be from the lower value of time t1 to the higher value of time t2, and this will be the total impulse of f. Total impulse of f in that interval t1 less than t less than t2. Maybe I can put equalities, and that's it. So these are very trivial things, but I thought that we should just have all of these for the sake of completion. So this is how you will find out the total impulse of a force. Now related to this idea is the idea of impulse momentum theorem. So what is that impulse momentum theorem? Now it says that if there is an object of mass m, suppose there is an object of mass m that is moving with some velocity v, like this, to the right hand side, let us say, some velocity v, and there is some force acting on this object. Maybe the force is acting like this, F, and this F is the resultant of a large number of forces which are acting on this object. Then F dt is equal to mdv, or you can say integral of f dt is equal to m times v final minus v initial. After you integrate the right hand side, you are going to get v, and when you insert the limits, you are going to get v final minus v initial, and mv final is p final and mv initial is p initial. So you are going to get delta p, p final minus p initial, and on the left hand side there is this j anyways. Now this may seem to be a very trivial thing, and there is always a doubt that is going to appear in your mind as to why are we giving it a fancy name, impulse momentum theorem. But we will see that applied to one individual particle it's not very interesting, but applied to maybe a system of many particles, it gives you a very interesting answer, or in fact it gives you interesting answers based on whatever the statement of the problem is, and we'll be solving a few of them afterwards. But then please keep in mind that when you apply this impulse momentum theorem for a system of particles, then the terms will change a bit. On the left hand side will be just the external force acting on the system of particles, and on the right hand side you will get the velocity of center of mass here. So applied to a system of particles, you will get on the left hand side F external net dt is equal to m, and the mass here will be the total mass of all the particles. So I should say summation of m times dv center of mass. You are going to get this entire equation, which is very interesting because then the internal interactions between the particles do not even appear. You know that the internal interactions will not appear because when I write all those internal interactions, and if I add up all the terms, all the force into dt terms on the left hand side, the terms containing those internal interactions will cancel off. So what this means is that if you have two blocks, let us say, that are sliding over each other and there is friction, and the lower one is also kept on a floor and it is moving on the floor, if I just look at the friction between the lower block and the floor, that is going to give me information about what is happening to the center of mass of the system. I don't even have to think about the friction between the two blocks coming into picture. So this will have very interesting applications when we are applying it to a system of two or more particles. We will see it, but please keep in mind that we will use this thing called impulse momentum theorem. Now, related to the idea of impulse and impulse momentum theorem is the idea of impulsive forces. So you have something called impulsive forces. Now, what are impulsive forces? You see that sometimes, like say for example in a game of cricket or maybe in a game of football. So let's take the example of cricket first. You have a batsman who is waiting for the ball to come, and as the ball comes, he hits the ball, and there is this ball that is in contact with the bat for a very small amount of time, very small amount of time, maybe milliseconds, less than that. And in that amount of time, there is a finite change in the momentum of ball, because we know that initially it was moving somewhere else, its mass was some number, its velocity was something, and we could find out mv initial, and finally the ball is flying off to a very different place, the same mass but a very different velocity, and we know that there is a definite finite change in momentum of this ball. But that definite finite change in the momentum was brought about by a force that acted for a very short amount of time. So what can we say about the nature of the force then? So keep in mind that sometimes a finite change in momentum is brought about in an infinitesimally small amount of time in fact I should put interval also. In an infinitesimally small amount of time interval, for example in a game of cricket, so bat hitting a ball, or perhaps a footballer kicking a football, so football being kicked. So again, there is a very finite amount of change in the momentum of football, but the time duration for which the foot was in contact with the football is extremely small. So there is an extremely small, infinitesimally small amount of time interval, and there is a finite change in momentum that implies that the force that is acting on the ball in both these cases, either the bat hitting the ball or the foot hitting the football, the force that is acting on the football or the cricket ball is extremely large, and such a force is called an impulsive force. So in such cases, F is equal to delta P divided by delta T, which in fact tends to 0, is usually tending to infinite. So this force, a very large amount of force acting for a very small amount of time, is usually referred to as an impulsive force. A very large force acting for a very small interval of time is called an impulsive force. So forces that can take huge values. So that will make us exclude certain forces from the list of impulsive forces. Which forces cannot be impulsive? Forces that cannot be impulsive will be forces like weight. Weight of an object is a constant. So if I talk about maybe non-impulsive forces, I can talk about weight. It's a constant force always. So an object of mass m will always have a force mg acting on it, and that will never change. It can't become more than mg at any point of time. So there is no way that this can become extremely large even for a small amount of time. So this is gone. Then we have studied about spring forces. Spring forces are incapable of changing suddenly. So they always take some time to change, and that's why they can't be impulsive forces. So you have spring forces can't be impulsive, or any other constant force, let us say. So what kind of forces can be impulsive then? The kind of forces that can be impulsive are those that can undergo huge changes in their magnitude all of a sudden. So sometimes we say that normal force is impulsive. Normal reactions are usually impulsive. For example, take the case of a ball being hit by a cricket bat. Now when the ball and the bat are in contact, there is a certain normal force acting between the bat and the ball, and it is this normal force that gives that huge impulse to the ball that changes its momentum by a finite amount. Or maybe when you have a footballer kicking a football, the foot is in contact with the football for a very small amount of time, and it is that kick, the force by the foot on the football, that gives a finite change in momentum to the football. So that normal reaction between the foot and the football is an impulsive force. And if normal reaction is impulsive, then the friction can also become impulsive, because in some cases there will be a rough surface and there will be an object on the rough surface, maybe like a ball, and this ball is in contact with the surface for a very small amount of time. But in that small amount of time, because the normal reaction is impulsive, there will be friction that will be impulsive, and that friction will apply a torque on the ball and the ball may start spinning. That's how balls spin in a game of cricket. So when the bowler bowls the ball falls on the ground for a very small amount of time, and in that small amount of time it bounces off. So the normal between the ground and the ball is impulsive, and because of that the force of friction between the ground and the ball is also impulsive, because it will be mu n, the maximum force of friction, and assuming that there is slipping happening over there. And then what happens is the ball gains a certain amount of spin in a certain direction. So please keep in mind that normal forces can be impulsive. So by extension, frictional forces can be expansive. Then string forces can be impulsive, because string forces can change their values suddenly. So you have the example of bungee jumping for that. Now in bungee jumping we usually use an elastic cord, and what that elastic cord does is it slows down the fall gradually. So you have a person whose waist is fitted into that elastic cord, and this person falls down, and initially the cord is just hanging slack in the air and the person is falling down, and then at a certain moment the distance of man from the hilltop. So let me first show you how a hilltop is. So here is the hilltop from where the person is going bungee jumping, and there is a cord around his waist, and that is maybe attached to something over there. And as the person jumps, of course you should not have the support here, you should have the support here, otherwise the person will try to come back like the pendulum and hit the cliff face and will die. So the support is somewhere here. But then what happens is, as the person jumps, he is in mid-air somewhere like this, and the cord is still hanging loose to some support there. And then at a certain moment, when the man is sufficiently below, somewhere like this, the cord becomes taut, and the man is not stopped there, the cord elongates, and the man keeps on going down. The man keeps on going down, and the cord stretches, and the cord has got certain amount of energy stored in it, elastic potential energy, and the man is then pulled back by the cord. Fine, so all this happens. Now imagine replacing this elastic cord by inelastic cord, our ideal strings, inextensible. So what will happen? Until here it's fine, until here also it's fine, the string is slack, but then at this precise moment when the string becomes completely taut, the backbone of this person is going to break and the person is going to die. The reason? This man had a very huge velocity just before the cord became completely taut, and just after the cord became completely taut, because the cord was inextensible, the person was stopped all of a sudden. So huge momentum going to zero in a very small amount, in a very small amount of time, a very large force acting on the man, and that large force is enough to break his backbone. And these kind of accidents have happened, where the cord loses the elasticity over time, where the cord in fact breaks in between, after a few runs here and there. So keep in mind that string tension can be an impulsive force. So normal reaction is impulsive, frictional forces are impulsive. Now we have string tensions which are impulsive. And so on. So there is a list of non-impulsive forces, there is a list of impulsive forces, and there is a class of forces that won't be impulsive at any point of time, any constant force, weight or spring forces, etc. We know that some forces can be non-impulsive, like you have normal force between a block and the floor. It can be non-impulsive, it can be equal to weight if the block is simply resting on the surface, but it can also be impulsive at times if the ball is rebounding off a surface, let us say. Frictional forces can be non-impulsive. There is no rule that says that they have to be impulsive always, but if the right set of criteria are met, then frictional forces will also become impulsive. So please keep in mind that there are some usual forces that will become impulsive in certain situations, and that small amount of time that we are speaking about, during that small amount of time on a certain object, there may be impulsive forces, there may be non-impulsive forces. So you take the example of a ball bouncing off a floor. So here is a floor and there is a ball that comes in. So there is a red colored ball that will come in from here, will hit the floor like this, and then will rebound in that direction and will go off like that. So in the small amount of time that it was in contact with the floor, there was one impulsive force acting on it, which was the normal force. Maybe if there was friction, then there was also an impulsive friction which will impart some kind of spin to the ball. But weight of this ball was also acting on the ball, and that weight was non-impulsive. So you have got a combination of impulsive forces and non-impulsive forces acting on this particular ball. Impulsive force is N, and non-impulsive force is weight. In fact, if you now notice, the N that I have drawn is incorrect, because this N should be huge. It should be a huge arrow. It should keep on going. It should be 1,000, 2,000 times more than the weight of this ball. Who knows? We have no clue. We'll have to find out based on the amount of time for which the ball is in contact with the floor. But whenever that happens, you will have to calculate the impulse due to this N and impulse due to this weight for that small amount of time, and the impulse due to this weight will be usually neglected. So keep in mind that whenever impulsive forces are acting, the impulse due to non-impulsive forces is neglected. You will see that when you frame equations with the impulse of even weight being there in those equations, the equations will be a bit more challenging to solve. So what we will do is we will throw away the impulse of these non-impulsive forces and then just try to find out the answer using impulsive forces effects.